In this video, we're looking at factorials and permutations under the lens of combinatorics. So we're starting off with an example today. Consider the HB department wanting to display 5 new trophies along a shelf in the school foyer. So we have 5 shelves, or 5 spots in a shelf, and we want to calculate how many different ways can we set up these 5 trophies. So in our first option, we're going to have to pick one of those 5 trophies. Then that trophy is no longer in play. It's been positioned. We have 4 trophies that are left to pick for the second option, and this reduces as we go down. The number of ways we can do this then uses the multiplication principle. So we multiply these together, and we get 5 times 4 times 3 times 2 times 1, which is going to be 120 different ways. So because we do this so often in combinatorics, reducing the number by 1 as we multiply it, mathematicians are a tiny bit lazy, and we like to have notation for stuff that we commonly use. So instead of writing out 5 times 4 times 3 times 2 times 1 every single time, we yell the number 5 factorial. It's an exclamation point, and all it means is take the number, multiply it by one number less until you get down to 1. So the general case is called n factorial, written as n exclamation point. That's going to be n times itself minus 1. Going to continue on until you get to times 3 times 2 times 1. Okay, so that's the product of each integer from n down to 1. A special case of this is 0 factorial, because 0 factorial is equal to 1. So evaluate the following. 7 factorial is equal to 7 times 6 times 5, all the way down to 1. I'm going to write the 1, but you'll soon realize that the 1 is unnecessary because anything times 1 is itself. So you really could stop at 2. That's going to evaluate to 5,040. We can see if you were to, maybe not graph, but if you were to list the points of x factorial, where x was constantly changing and was natural numbers, you can see by x equals 7, we're already in the 5,000s. So this gets very big very quickly, and we'll see that with 13 factorial. So 13 factorial, we're going to list out all these numbers, 13, 12, then we're going to get lazy, and we're going to go times 3, times 2, times 1. And we're saying, yeah, you can fill in the gaps there. You know it's going to be 12, 11, 10, 9, 8, 7, 6, 5, 4, and then 3, 2, 1. That equates to 6,227,020,800. So we're in the billions by only the 13th instance. And this sort of explains why things like the lottery are such low odds. You think about having 40 options for lottery balls, and then you slowly or you're picking each one, and then you have fewer to pick from. By 13, if we were just drawing 13 balls from 13, there would be a 1 in 6 billion chance of winning. But they don't do that. They have 40 numbers to choose from, and they choose, I think, 10 or 12 of them. So that's even lower odds than this. So if we move on to our next example, 8 factorial over 5 factorial, factorials have a fancy property that if you have 2 factorials over the top of each other, well, this is going to be 8 times 7 times 6 times 5 times 4 times 3 times 2. This part here is 5 factorial. If I extend it one further, it's going to be 6 factorial. So because factorials have this sort of recurrence to them, where I'm just adding another number in front, if we divide factorials together, we actually get portions of the factorial. So this just becomes 8 times 7 times 6. This will be extremely useful later on for when we're looking at not picking all of the trophies in the shelf or all of the numbers out of 13. If we're just picking 3 of them, we'll have to be using this property. But we'll look into that a little bit more detail in later videos. So 8 times 7 times 6, that's just going to give us 336. For the last one, we're looking at it a bit more abstract. So n take 1 factorial over n take 3. We're assuming here n is a natural number, so any number that's an integer that's positive. So if we were to apply this factorial, we're going to get n take 1 times n take 2 times n take 3, so on and so forth. But n take 3 we have on the denominator, so I could write that as n take 3 factorial, and that's going to be over itself. So these two are going to cancel because they're all the same number, n take 3 times n take 4, all the way until it gets to times 3, times 2, times 1. So all we're left with is this n take 1 times n take 2. Are we going to get any more information if we expand these brackets? Not really, so we just leave it in factorized form. So we can see if our value of n was, say, 4, this would be 3 times 2, which would be 6. Okay, permutations. So to select 3 letters from 7 where order is important, the possible arrangements is going to be 7 for the first one, then we have 6 letters left, and then we have 5 letters left. Well, this 7 times 6 times 5 looks awfully familiar to this 8 times 7 times 6 that we looked at in part C. So let's think of another way that we could have written that. So if we start with 7 factorial, we're going to have to divide by, well, what would be left is the 4 times 3 times 2. So that's going to be 4 factorial. That's the same as what we've just calculated out. And you might think, well, why don't we just always do 7 times 6 times 5? Well, sometimes it's not just going to be 3 numbers. It could be choosing 100 letters from 1,000 options. And at that point, we want to rely on the formula, something that we can plug into our calculators. But in this instance, 7 times 6 times 5 is just going to be... so that's going to be 30 times 7, which is going to be 210. So this is our generalized form for this. The number of way of choosing r things from n distinct things is given by the rule n times n take 1 times, and then that pattern continues until you get to n take r plus 1. So in our instance here, it was choosing 3 things from 7 distinct things. We started at 7, we went to 7 take 1, which is 6, and then we stopped at 7 take 3 plus 1, which is 5. So the other way we can write that is just n times n take 1 times so on and so forth until we get to n take r factorial over n take r factorial. So this is just written as n factorial over n take r factorial. So you can see we sort of combined this n take r factorial with all of the things that were before it. So because this is adding 1 to it each time until we get up to n, that's the same thing as starting at n factorial. So when working in this example, we cancelled those 2 parts in the numerator and we just had 7 times 6 times 5, but our general case includes those 2. The 2 special cases that we have are NPN, so NPN and NP0. So if we had NPN, R is going to be n, so we'd get n factorial over n take n factorial. That's 0 factorial, which we know is 1, so we get that that's just equal to n factorial. And then NP0, we're going to have n factorial over n take 0 factorial. which is going to be 1, which makes sense. There's only one way that you can choose no things, and that's by choosing no things. And there's only one way to choose all the things, and that's by choosing... and then there's n factorial way of choosing all the things, because your R value is n, right? If you have to choose 7 numbers, and you have 7 to choose from, it's going to be your 7 times 6 times 5, all the way down to 1. So that's why these two make sense. Okay, let's look at this in practice. So calculate the number of permutations for 6 permute 4 by expressing it in expanded form. So 6 permute 4 is going to be equal to 6 factorial over 6 take 4 factorial, which is going to be 6 factorial over 2 factorial, which is just going to be 6 times 5 times 4 times 3. So we lose the 2 because we divided by 2 factorial. And that is going to give us 360. So that was part A. For part B, we're asked to write 8 permute 3 as a quotient of factorials and hence evaluate. Okay, so that last one, if it's just expressing it in expanded form, I'd just be looking at this 6 times 5 times 4 times 3. So I actually did part B's methodology for both of them. That's fine. Let's just calculate 8 permute 3. So that's going to be 8 factorial over 8 take 3 factorial, which is 8 factorial over 5 factorial, which is going to be 8 times 7 times 6. We already know this from earlier. That's going to be 336. Okay, example 8. The netball club needs a president, secretary, and treasurer. From the committee, 7 people have volunteered for these positions, and each of the 7 nominees is happy to fill any one of these 3 positions. Determine how many different ways these positions can be filled. So, recalling the rule for permutations, we're looking at NPR. What is our value of n? Well, we have 7 possible people to choose from. How many spots do we need to choose? 3. So this is going to be 7 permute 3, which is the same as 7 factorial over 4 factorial, which is going to be 7 times 6 times 5, which is equal to 210. So we then need to answer this with a sentence, because 210 is not our answer. Our answer is there are 210 different ways to fill the 3 positions. Okay, part B. For 3 years, the same 7 people volunteered for these positions. Determine the probability one of them is president 3 years from now. So the total number of ways the president's position could be filled, that would be given by n of the complete set, is going to be equal to 7 times 7 times 7. So what we're saying there is there's 7 people that could be president year 1. So let's call this year 1, year 2, year 3. So each year, one of those 7 people is going to have to take that position. So in total, there's 343 different ways that president's position could be filled across those 3 years. The number of ways for action A, which is one of them being president 3 years in a row, is going to be 7, right? Because either person 1 is going to be there 3 years in a row, person 2 is going to be there 3 years in a row, all the way up to 7. So there's only 7 options based off the 7 different people. So our probability is going to be 7 over 7 times 7 times 7. And I've written it like that because then we get some cancellation. So this just becomes 1 out of 49. So you have a 1 in 49 chance of filling the president's position 3 years in a row. So we write that out. 1 in 49 chance that the same person fills in the president role 3 years in a row. Right, that's off to the side there. Okay. The other way we can look at arranging with this idea of permutations is arrangements in a circle. So in how many ways can 7 people be seated 4 at a time on a bench? This is just like everything that we've been looking at. You've got 7 options for the first one, 6 for the next one, 5 for the next one, and 4 for the last one. So 7 times 6 times 4 is going to be the same as 7p4, which is 840 ways. So we have 840 different ways 7 people can be seated at a bench. What about if they're instead at a table? So then we have the issue that these 4 arrangements, for example, are all the same, right? A is next to D, D is next to C, C is next to B, and B is next to A in all 4 of these arrangements. So the number of arrangements is going to be 7p4, but we have to account for these quadruple ups of 4 of them being the same. So all we do is divide that answer by 4. So in our case, that's 840 on 4, which is 210. So in general, the number of different ways is NPR on R, right? Because our circle has 4 objects in it, and that's our R value. So let's determine this in example 9. Number of different ways, 8 people, 5 are to be seated at a round table. So that's going to be NPR on R, which is equal to, we have 8 possible people, we have 5 places for them to sit. So that's going to be 8p5 on 5, which is equal to 6,720 on 5, which is equal to 1,344. So a lot of different ways to seat these people. Part B. Each table receives 1 lucky door prize and 1 lucky seat prize. Determine the probability of the same person at one table winning both. Now, before we can answer this, we need to sort out what is a lucky door prize and what is a lucky seat prize. So a lucky door prize goes to 1 person out of everyone that's in the building. So we have two prizes, and each prize can be won by any one of the 5 people. So our number of possible ways is going to be the number in the sample space. So we have 5 different people that could win the lucky door prize, because it says each table. Sorry, that was something I missed in the question. Each table receives a lucky door prize and a lucky seat prize. So 5 people, 1 of 5 people could win the lucky door prize, 1 of 5 people could win the lucky seat prize. So there's 25 different ways that people could win this. To win both prizes, there are going to be 5 people that could win both prizes. Right, that's going to be based off the 5 people that are sitting there. So our probability of the action A is going to be n of A over n of the sample space, which is equal to 5/25, which means there is a 1 in 5 chance of winning both prizes. Okay, so if we look at that, we're kind of saying that it's irrelevant where you're sitting. Everyone has equal odds to get both the lucky door prize and the lucky seat prize, which makes sense because each prize has the same odd of happening. So if you compound those odds, that's not actually going to do anything. It's not going to make it more rare. It's not that the door prize is 1 in 1,000. It's still 1 in 5. So the odds of anyone getting both is just 1 in 5. So that completes this video. Next, we'll be looking at what happens if we put restrictions on these permutations.